Hey folks, so I wanted to just do a walkthrough of a program, a very simple program that I built for the Curiosity PIC32 MZ space EF development board. It's basically just one of the Curiosity boards that Microchip makes, which is really honestly great of them to make boards like this. They have integrated programming and debugging capability headers programmed onto the board so that you actually don't need to use a external programmer like a PIC kit or something like that. So it makes them a little bit more portable, and if you don't have a lot of time or a huge amount of space to dedicate to the actual process of learning about these, it's literally a $50 board and a USB micro connection to your computer, and that's all you need. It has integrated LEDs, a couple switches and buttons, and just a few features like that. Obviously, the existing RAM and memory and stuff like that that it has on the chip. This board in particular also has Wi-Fi, which is a really interesting capability for a chip like this. To think back, 5 years, it would have cost you maybe $150 for a Wi-Fi, add-in piece, not just to have a $50 board that included a chip and debugging and all the stuff. So it's amazing how prices have changed in even the last 5 years. Programming, however, has not changed all that much in the last 5 years. So the reason I kind of have the 5 year time frame here is that it is 2018, and the last time I was really working on this stuff was 5 years ago, 2013. So I just sort of want to go over a few of the differences. Back then, we were not using MPLAB X, for one thing. It was MPLAB 8, I think, or maybe even a lower version than that. And one of the differences you have for your include file here is that this is sort of an intelligent include file that looks at your configuration up here. So this is the configuration that I have set for this project. I do have this running on this starter board, the PIC32 MZEF starter board. But you can see that I selected the device up here. So basically what this include file does is it actually looks to see what this device is, and it includes the header file for that device. You can actually tell this to a certain degree too. I believe when you press Control and click on one of these, you'll actually see it's got this header file that is the exact chip that I'm talking about. And it's already linked in there in the background. So you can see that, if you wanted to see, what exactly these TRIS registers were connected to or what the attributes are. And I mean, it's a dense file. Like I said, it was 2 megabytes just to load it, but it can help if you do have any specific questions. And you can see at the top that this is, except this is for this processor's header. So, and it was 2015. So this processor is a relatively new processor. It has a few of the other features on it. It's, make it really interesting to use. But again, I mean, 2015, that's still 3 years old. So, like I said, the innovation in this space is not incredibly fast as far as the development. The costs have definitely gone down, though, which is really awesome for an at-home hobby kind of programmer, thinker person. Obviously with the advent of the Raspberry Pi, I think the first Raspberry Pi was launched about 5 years ago. That's one of the competitors, obviously, depending on what you're looking for. Obviously, Raspberry Pi is built on ARM architecture, which you're running Linux, your overhead it's to a very large degree a different animal. if nothing more than just talking about multi-threading. For example, this chip is, it's a single processor. There is no real multi-threading at all. It's a, single threaded, when interrupts happen, and they can, I mean, if you sort of want to look at it as multi-threaded that way, but it truly really isn't, because all other threads stop execution. So versus some, like today's processors, for example, they will interleave, two threads and execute an instruction, like a few instructions here, go back, execute a few other instructions. And it really, the reason you would want to do that kind of goes back into, sort of more of the core CPU architectures, and, well, honestly, and the fact that memory is usually the thing that the processor is waiting on. So the processors are quite frequently sitting at idle, even when you're trying to run them as hard as you can, because they're waiting for memory to be brought from RAM through the cache systems and to registers to be acted upon. Especially as efficient as some of the really high-end processors have gotten, that they're actually executing multiple instructions per clock cycle. So to have memory available is really the hardest thing. So that's a lot of the reason, I mean, not to digress, but that's a lot of the reason that Intel and AMD are running multiple threads per processor, is because they realize that the processors can usually handle more of the load than you can have data available. So they have these multi-core processors, multi-threaded processors that they're usually running 2 threads per processor, just because, when one thread is waiting for data, the CPU goes idle and it switches to the other. And then obviously they have some method for not starving one of the threads if you did happen to have data. For example, your program was extremely simple and just, counting, up, a register all the way, from, 128-bit register, just counting from 0 to very large. Obviously there's no memory access needed for something like that, but it would access the processor. So that is actually a terrible way to do a delay loop in a modern day processor, because one of the things that you get with a multi-threaded processor is things like mouse movement. So if you think back to the late 90s and computers then, one of the things that would happen when your computer was really overloaded is your mouse would stop working. And Microsoft and Apple, mostly Microsoft, really understood very quickly that this was a customer dissatisfier. That anytime the mouse stopped moving or was like jerky, so it'd be like move from here to here to here as you're like trying to like move around the screen, and you just couldn't do that. They have moved the thread for the mouse to a extremely low separation on the thread side, so that it is, I mean, essentially like it almost runs as a separate operating system. I mean, it doesn't. I mean, that's a crude way of saying it, but Windows can be completely loaded out, completely unresponsive. Clicking on start won't work. Clicking on anything won't work. Like every window has frozen, and your mouse will still react. And the reason is just the low level that they're running this mouse thread at, and the switching that's happening is really so separated from the program code in a separate thread that your CPU can literally be maxed out trying to perform other actions, and the updating of the screen and the mouse cursor will still get processor time and memory. So, and really the processor time is what you're looking like. Like I said, if you were to count an integer, from 0 to 128 bits, you're maxing the processor. If you would have done that on a 1998, Windows 98, Windows 95 computer, your mouse would have frozen, and you wouldn't even be able to cancel the program. So now they have a few things where you can actually do that because of multi-threading. So, is multi-threading a great thing? It depends on what you're doing. For things like this, you don't really need it. And it's actually much more convenient to debug single-threaded programs when you're debugging multi-threaded programs, usually up here somewhere you're going to have a little drop-down box sort of like this that shows all of your active threads. So if you're working on Windows and C++ or something like that, and you have a, there's a lot of reasons and a lot of different ways to configure threads, but generally communication between threads is difficult. So usually you have some sort of thread that does job queuing, and then other threads that are actually execution threads that read from the job queue. So it'll say, job queue thread and then execution thread like 1 through 10 or something like that. That's a pretty standard way if you were going to try and use all of the processing power in a modern computer, that you would have like I said, one queue thread, one task thread, and then execution threads, many execution threads. And literally, you would want to have an execution thread per processor thread. So a 4-core, 8-threaded processor, you're probably going to want to run, 7 of those, maybe 6 if you want to save a thread for the CPU, for the operating system, just to make sure you don't get too lagged out. Because obviously the operating system is going to take some time. It will preempt some of your code. So that's one of the tuning things that you can do. But none of that really applies here. So and the reason it doesn't is because of preempting. In interrupts specifically. So what will happen is anytime you run your code and like an interrupt happens. So an interrupt being something that is like an external event that causes your processor to execute some different code. So anytime an interrupt happens on one of the PIC series, PIC32, PIC16, PIC8s, well, I guess it's really PIC10s, PIC10, PIC12, PIC16, PIC32, PIC24. Any of those, basically what it does is it just steals the essentially CPU from your currently running program or loop, and it executes this other loop until the execution returns. So essentially, it just allows you a very small amount of processing to happen on that loop, and then it basically, once that loop exits, your processor will go back to running your main code. So as far as debugging those things, I'll probably get into that in a different video, but it's really as simple as just putting a breakpoint in the function that's called by the interrupt, because that's essentially what an interrupt does. Is you say interrupt calls this function, and you say, well, if it calls the function delay, you just put a breakpoint, right there, just put a breakpoint in the function, and then as soon as the interrupt is called, it'll hit your breakpoint, and there you go. You understand. So anyway, so the reason I was really getting into this video is, so largely I've said that things have changed quite a lot since in the last 5 years, including this header file. I kind of got off on a tangent on the header file here, and showed you the actual header file that is going to be included. One of the other things is the configuration of the chips, and that's what all this is at the top here. This has changed quite a lot too. And this is going to be partially based on, I would actually say largely based on your compiler. So the compilers that you're going to run, there's 3 different compilers that you have essentially for the PIC chips. You've got the XC32, XC16, and XC8. So that's essentially for the 8-bit, the 16-bit, and the 32-bit processors. Now, the reason that each one of those is different is they're actually a totally different C language. So you're going to have different ways of setting your config files. You're going to have different ways of running delay loops, a lot of the different ways of setting registers. Everything it can be different in these. And so you really need to keep that in mind, that if you are going to microchip and you want to, have a collection of different chips and you're going to be running different things, obviously in general, the 8-bit chips are going to be the cheapest, with some of the cheapest of the cheap 8-bit chips being under $1 a chip. And they still have, I/O pins and everything else. I mean, it's still a functional chip, for sure, versus, some of the more expensive 32-bit chips can be almost $20 per chip, so 20 times as expensive. So it really kind of depends on what kind of processing power you actually need for your project. However, the thing to keep in mind is that instead of learning one new language here, as far as C programming for embedded devices, you're really talking about 3 languages. XC8, XC16, and XC32, and they are all different. Like for example, like this program I just got working, and it's actually even not quite 100% working. And basically, all I'm doing here is really trying to turn on and turn off an LED that's on this board. So I mentioned that I have this PIC32 MZEF starter board over here, and you can see when it says over here, you see it says XC32, and I actually have 2 versions of that XC32 installed. I have version 1.4 and 1.44. Now, when you take code from online, like if you have some place that if it's Stack Overflow or Microchip or some other site that's trying to educate about programming in PIC, it's really important to know what version you're running, because function names change, functions become available, functions become retired. I struggled a lot in the beginning with certain functions not existing and not really knowing what I was doing. A lot of the difference was literally just the difference between the version 1.44 and the version 1.4 of the compiler. There are obviously many other versions that you can download. Currently, as of today, 1.44 is the current. So if you go to the Microchip site and type in XC32, this is the one they're going to have you download. And you can download the legacy ones. So for example, like you see here, there's a link that says download latest. The reason is because if you installed this program a couple years ago or whatever, you're going to have a lower version, and you could continue happily using that version for however long you want. And then, until there's some function or some chip that supports something that a new function is needed, in order to help define that or something like that. So that's why they have this link here. Is that generally, this is one of the things that once you get set up, you don't really upgrade these all that often. And I think that's part of the reason why they have the little yellow versus green indicators here, is that even though I've got this 1.4 active for this program, I think it has a yellow here just to show that it's not maybe the most current version. I would say you run into this in a lot of software programming, but having the most current version is actually not usually a good idea. For example, I remember when I was in college, we were trained in Visual Studio programming, and when we were trained, we were using the brand new version that was released from Microsoft, and that's the version that Microsoft either donated or was purchased by the school, and the school was like, we need to stay up to date on this. And when I got my job, we were 2 version cycles behind the version that I was trained on. So I had all these newfangled features and things like that that I was ready to use that didn't even exist yet, because the version that the company that hired me was using was still, essentially 7 years out of date. And this is a very common thing that happens, for business and for all sorts of projects, because, it's risky to upgrade software like that. When you have something that is stable and works, and you have a lot of code that's programmed in it, the last thing you want to do is just say, oh, well, what we're going to do is we're going to recompile all of our code using a different compiler. That's when you already have something that's working, that is never going to really just help you out of the gate. Conceivably, there could be some performance enhancements and stuff like that happen with additional compiler versions, but there's also the risk that something that you did before doesn't work now. And when you're talking about a company or even personally, the last thing you want to do is just be digging through and trying to figure out, why this doesn't work, and what the difference is. And that's why I'm saying specifically as a beginner, it's really important to get the correct version of the compiler, because if you have some code that was compiled on version 1.35 or something like that, you want to download the compiler for 1.35. And you want to compile that code on the compiler that the code was expecting, because you are probably not going to know enough to be going through and doing the troubleshooting of upgrading the version, because you really need to know if it's written for 1.35, you really need to know 1.35 in and out, and the destination 1.44, for example, in and out, to know what the changes are, what's happened between there, what functions have changed, and what updates need to be made. And that's one of the things that I ran into is I really didn't. And it makes you dive in way deeper to code than you would really need to, just to sort of have an idea of, trying just to try and get it to work, to try and get it to run. So, as a beginner, the goal is always, let's try to get this to run. Like, how do we get something to actually function? And once it's functioning, then we can take it from there and we can actually do some tweaking. All right, so I've spent quite a lot of time here kind of going over the setup of this. Hopefully I've scrolled slow enough that you guys can kind of see everything in here. But basically, we have the include file here at the top, and then a whole bunch of config, which I'm not going to go into what it does, because honestly, I don't even know all of what it does. And then we have two functions that I found on a forum, which you would never do in Windows programming. Essentially what this is it's a delay function that runs a loop that counts. Like I said, this is totally what you would absolutely never do in Windows programming, but you can get away with it on a microchip because, well, essentially, like I said, because of the multi-threading problem. So essentially what this is doing is it's putting every single ounce of CPU power that this chip has around counting. Which takes time, and the counting taking time, because we're counting to 100,000 over and over and over again. What is this, like counting to 100,000 10 times or something like that, not to mention the function call here. And really, like I said, this is one of the ways to not be memory bound, that your CPU is just crunching as hard as you can. So it does actually create a delay, and eventually it will return. So you will actually execute through all of these loops eventually, and that is your delay loop. So if you ever want something to happen and then you want to break and then you want something else to happen, you want some sort of a delay, and this is an acceptable but very, like I said, crude and not Windows, Linux, Mac, iPhone. You pretty much wouldn't do this anywhere else except for on a microprocessor like this, because otherwise, if you were to do this on an iPhone, you are just chewing through battery like crazy right here, because the processor is running. It is running fast and hard, and it's really kind of bad, because if you have this in there, not to mention that it's going to make your UI on your iPhone completely freeze while you're running this, unless it's a multi-core processor, which some of them are and some of them aren't. Again, really bad idea in general to do this. So we'll talk about other ways that you would do this later. And here's the main. So the main is very small. Basically, just setting the TRISC registers, setting the latch registers, calling a delay, setting the latch registers again to 0, calling a delay, and then looping. So this is a while one. So it just loops, and never returns. So basically, that's its goal. The processor is running essentially as hard as it can for the entire time, and it just is using these delays to separate these latch calls right here.